every single day you're interacting with this massive invisible force. Every click, every search, every app you tap open, it's generating data. It's just absolutely everywhere, and the amount of it is just exploding. So today we're taking a deep dive into that huge ocean of information. We're going to explore what data really is, why it's become so important, such an indispensable tool, and also how these advanced fields like data analytics, data science, and artificial intelligence are turning it into powerful, actionable insights. Our mission really is to help you navigate this massive digital landscape and sort of reveal how data isn't just abstract numbers. It's actually a critical tool for understanding and honestly profoundly improving our world.
It really is an incredible journey, this transformation. Over the course of this deep dive, we'll kick things off with the basics, the foundational stuff, what data is in its simplest forms. And then we'll explore its key differences, the different types. From there, we'll scale up to this phenomena of big data and what really defines it, its characteristics. Then we'll pivot a bit to how we actually pull meaning out of all this information that's through analytics and visualization, before finally venturing into the really cutting-edge world of data science and AI. And crucially, I think we'll unpack the fundamental shift in how computers now learn through data mining. It's a concept that's changing, well, everything.
Right, we talk about data constantly, but let's actually grab some and see what it's made of. At its absolute core, data is basically just raw information. And for anyone who might think, oh, data, that's just crunching numbers, it's way more diverse than you might imagine. It can be facts, stats, recorded voices, photos, names. I mean, the source even mentioned dance moves. It's all just information, right? Recorded in different formats. It's like a universal language for observation.
Yeah, and what's truly fascinating is how that raw information turns into, well, tangible power. Data is important for just so many reasons. Fundamentally, it lets us move from just intuition, like a gut feeling, to actual evidence. And this isn't just about, abstract statistics. It's about improving people's lives.
Yes.
Like tracking service satisfaction or spotting trends that let us step in and help. It's about making informed decisions.
Yeah.
Moving away from assumptions and using actual verifiable facts to plan and adapt much more effectively.
So it's really about that shift from intuition to evidence.
Right.
Which also means being proactive, I guess. Data can be that kind of early warning system, like the check engine light in your car, helping you spot small issues before they, snowball into huge crises. Think about things like incident reports, potential medication errors, or even gaps in service data can shine a light on those vulnerabilities. And it's how you really measure what works, isn't it? That new program actually help? Data lets you figure out its effectiveness, fine-tune your strategies, or scale up what's genuinely successful.
And this ability to understand what works also brings up the critical question of why it works. Data helps us find those root causes. So, if staff turnover spikes, and at the same time incident reports go up, data gives you the clarity to connect those dots. It reveals not just the symptoms, but the underlying reasons. And on a kind of broader scale, it really strengthens advocacy. When you're trying to get funding or pushing for policy changes, backing up those compelling human stories with hard data, that gives you an undeniable voice.
That is powerful because using data to explain decisions, whether they lead to wins or maybe reveal some challenges, that builds huge trust, right? It shows your actions are grounded in reality, not just like gut feelings. And it forces you to be strategic, focusing your limited resources where they're most needed, avoiding wasted time and money. Plus, data helps you spot high-performing teams or programs you can replicate and set clear, measurable goals. You can prove your impact to funders and stakeholders with real evidence. Ultimately, like our research highlighted, data is not about numbers. It's about the lives behind them. Every chart, every report, it really is a tool to improve care.
And this brings us to the sheer scale of information we're dealing with now. The global data generated annually has absolutely exploded. It went from around 2 zettabytes back in 2010 to an estimated, get this, 180 zettabytes by 2025. It's an incredible flood of information. And this fuels what we call data intelligence, which is essentially using data to analyze, understand, and, well, grow businesses. This includes everything from tracking internal operational data to analyzing market trends and forecasting for future investments. The goal always is to extract useful, relevant insights that guide better decisions. And to do this, the key components of data intelligence include big data itself, obviously data mining to find those hidden patterns, event processing, which means analyzing real-time streams of events to spot anomalies or opportunities, and online analytics, tracking user behavior on websites or apps for immediate insights.
Okay, so given this vast ocean of information, what does it really mean to make data-driven decisions? Is it just about having the numbers? It sounds like it's more about grounding your choices in facts, not just feelings or opinions. Like, imagine launching a new product because clear market demand data supports it. Or maybe changing services based on undeniable customer feedback trends you see in the data. Or scaling operations precisely where data shows there's growth potential. And to enable this, you often use something called a data warehouse. What exactly is that? Like a giant filing cabinet.
Sort of, yeah. Think of it like a highly curated, consolidated library of all your business history. But it's purpose-built not for daily transactions, but specifically for complex analysis and reporting. It makes it much more efficient than trying to dig through live operational systems. So yeah, it enables easier reporting, smarter comparisons, and much faster access to both historical trends and what's happening right now. It's all about reducing risk, increasing the chances of success, leading to consistent growth, delivering actionable insights, and making smarter resource allocation. The core idea, facts over opinions. It's about stopping the guesswork and starting to know. Right, and to effectively work with all this data, it's really crucial to understand its basic characteristics. We broadly categorize data into two main types, structured data and unstructured data. And the type of data you're dealing with really dictates how you analyze it and how you store it.
Okay, let's start with structured data then. That sounds well structured. So if it fits neatly into a traditional database table, with rows and columns, it's probably structured. This organization makes it really fast to search, sort, and analyze, I imagine. Like common examples: names, dates, addresses, credit card numbers, stock prices, maybe geolocation data. It's the kind of stuff that's easy to categorize and manage in systems like SQL databases or even just spreadsheets, right?
Exactly. A perfect illustration is a typical transaction record. For each customer, you might have a customer number, their last name, the purchase date, total spent, their location. Each customer gets their own row, and each specific piece of info gets its own dedicated column. That's structured data in action. And these are typically stored in databases, which, yeah, are essentially highly organized digital filing cabinets. And when we talk about relational databases, we mean databases where data is stored in multiple tables that are interconnected. This allows for incredibly powerful analysis by linking related bits of information together.
Gotcha. And then the flip side is unstructured data. So this is anything that can't be neatly put into rows and columns, not usually stored in those traditional relational databases like images, audio files, video, emails, Word documents, maybe social media posts. This kind of data must make up a huge chunk of the digital world now. And because it lacks that inherent organization, it needs totally different tools and approaches to analyze and get meaning out of it, I bet.
Absolutely requires a whole different toolkit. Now, beyond structured and unstructured, another really vital way to categorize data is as quantitative data or qualitative data.
Mm.
Quantitative data is all about the numbers. It's numerical, something you can measure or count, for example, height, temperature, blood pressure, the number of siblings someone has, or the time taken to finish a task, like 3.5 seconds. Understanding these distinctions is crucial because it dictates the kinds of statistical operations you can actually perform on the data.
Right, you can't average hair colors, for example. And within quantitative, you mentioned two subtypes: discrete data, that's countable whole numbers, like having 3 kids or 12 chickens, distinct values. And then continuous data, which can be any value in a range, including decimals, like someone being 1.75 meters tall or a car going 56.3 kilometers per hour.
Precisely. And then qualitative data, on the other hand, is descriptive or categorical. It describes qualities or characteristics that aren't inherently numerical. Examples like hair color, marital status, the texture of something, a smell, or the type of shirt someone's wearing.
Okay, and qualitative has subtypes too. Nominal data, those are just labels without any specific order, like married, single, divorced. And then ordinal data, where the categories do have an inherent order, like survey responses. Neutral, likely, very likely. It's like a ranking scale. So if we try that dog walk scenario from the source, a dog's weight would be quantitative, right?
Mm.
And the number of legs, also quantitative. But describing the dog as having short fur or black spots, those are qualitative.
Exactly. These distinctions are really fundamental to choosing the right way to analyze your data.
Okay, so now we know the different forms data takes. Let's talk about the sheer scale it's generated at, because that's where the real magic and the challenges begin. Everyone leaves this digital trail, right? And that's big data in action. It refers to the just Massive volume of data generated by our daily digital activities. We're talking everything from text messages and school records to your travel habits, your movie preferences, even all those internet-connected devices in your home. It's just mind-boggling how much information we all produce collectively.
Yeah, it really is. And while there's no single definition everyone agrees on, there are three core ideas that help us get a grip on big data. First, our actions generate data that can be analyzed. Pretty much everything people do online or with connected devices leaves a trace. Second, big data is known for its complexity. It's incredibly large, it moves incredibly fast, and it's super varied in its types. And finally, making sense of big data needs innovative tools because, frankly, traditional processing methods just can't handle its scale or complexity.
Right, they just weren't built for it. And these complexities are often summed up by what people call the 5 Vs. These are like
Yeah.
core characteristics that data scientists use to navigate and manage these incredibly complex data sets. First up, there's volume. Just the sheer massive amounts of data. We're talking exabytes, zettabytes, even yottabytes. This demands powerful tools just to store and manage it all.
Then there's variety. This refers to all the different types of data, both structured and unstructured, text, images, audio, sensor data, you name it. Your tools have to be able to ingest and process all these diverse formats and sources. After that, we have velocity. This is the speed at which data is created and moves. Think real-time social media feeds or sensor data streaming in constantly. Businesses need to process and react to this data very, very quickly, often with minimal delay.
Okay, volume, variety, velocity, what's next?
The fourth V is veracity. This one's all about the accuracy and trustworthiness of the data. And this seems crucial because inaccurate data, especially when you have so much of it, could completely mislead decisions. So data integrity is absolutely paramount. Couldn't agree more. And finally, there's value. Data is only helpful if it actually delivers useful insights or benefits. It needs to provide actionable or meaningful outcomes. Otherwise, all that volume and velocity, it's just noise, isn't it?
So, is it fair to say then that the biggest challenge with big data isn't just mastering one of these Vs, but the huge difficulty in balancing all five at the same time? Like, what happens if the veracity, the trustworthiness of your data is compromised? Does all that volume and velocity just end up amplifying bad decisions?
Absolutely, you've hit the nail on the head. That interplay is precisely the challenge. Compromised veracity can render even the highest volume and velocity completely useless, or even worse, actively harmful if you act on it. That's why managing big data isn't just about having enough storage. It's about having sophisticated governance and processing frameworks. Frameworks that can simultaneously handle the scale, the diversity, the speed, the trustworthiness, and ultimately the utility of the information. It really forces innovation, you know? New database tech, advanced analytical algorithms, the whole 9 yards.
Okay, so you've managed to collect all this data, you're grappling with the 5 Vs. Now what? How do you actually use it? This is where data analytics comes in, right? It's the process that helps us understand the past, explain what's happening now, and hopefully prepare for the future. Our exploration highlighted 4 main types of data analytics, and each one answers a very specific question.
That's right. Starting with the most foundational, we have descriptive analytics. This answers the question, what is happening? It gives you a clear snapshot of current or past data. Think your monthly revenue reports or daily stock performance. It's often the easiest type to visualize because it's a direct summary of facts. Next up is diagnostic analytics, which tackles the question, why is it happening? All right. This involves what's often called root cause analysis. It helps you investigate issues like, say, why shipments are suddenly slow or the unexpected side effects of certain medications. It really digs into the underlying causes.
Okay, so descriptive is what, diagnostic is why. Moving up the complexity ladder, we find predictive analytics. This answers what is likely to happen. So it uses historical data and statistical models to forecast future outcomes, like predicting sales figures or weather patterns, or maybe even figuring out when a machine part is likely to fail. It's about seeing what's probable down the line.
Exactly. And at the very top of this analytical pyramid is prescriptive analytics. This asks the most action-oriented question, what should we do about it? It doesn't just suggest actions based on the insights, it can even test potential outcomes before they happen. Think about Netflix recommending your next binge watch, or those sophisticated route optimizers that tell you the absolute best way to navigate traffic right now. So the progression from descriptive to diagnostic, then predictive, and finally prescriptive, it illustrates a clear path. More complexity equals more value. You move from simply knowing what happened to actually influencing what will happen.
And, they say a picture is worth 1,000 words, and that's precisely why data visualization is so incredibly powerful in all of this.
Mm.
Its main purpose is to help us explore patterns and trends that might just be hidden if you're staring at raw numbers. But just as importantly, it's about communicating those insights really clearly and effectively. It takes abstract or complex data and just makes it immediately understandable.
Mm. And this ability leads us straight into data storytelling, which is really the compelling combination of data plus visuals plus narrative.
Mm.
This trio, this combination, is what truly drives decisions, brings about change, and deepens understanding. The data provides the solid basis, the factual insight. The visuals, they reveal hidden patterns and simplify complex information. And the narrative, that explains the context, it highlights what truly matters, creating a cohesive, impactful message. It puts the so what into the data.
Right, gives it meaning. And to tell that data story well, you need to choose the right visualization types for different jobs. Like for showing proportion, you might use a pie chart or maybe a column chart. If you're ranking things, a bar chart is often really effective. To see trends over time, line charts or column charts are great. For illustrating frequency, how often something happens, again, column or line charts work well. And if you're looking for a correlation between two different things, a scatter plot or sometimes a bar chart can show that really effectively. It's all about picking the right visual tool to let your data's unique story shine through.
Right. And building on that power of analytics and visualization, we step into the really sophisticated realm of data science. At its heart, data science is about understanding the world through digital data, often discovering insights that weren't immediately obvious at all. It's a truly interdisciplinary field. It blends the scientific method, mathematics and statistics, AI and programming skills, data visualization, and that compelling storytelling we just talked about. Its ultimate goal: to pull real value and deep understanding out of those incredibly vast and complex data sets. As one insight put it quite nicely, data is a commodity, science turns it into meaning.
So, what do data scientists actually do day to day? It sounds complex. Are they the ones who prepare and meticulously clean up that often messy raw data, then analyze it, build sophisticated predictive models, visualize and present the insights, and crucially, predict outcomes using advanced tools like machine learning and artificial intelligence? It sounds like they're driven by a real curiosity, always asking why, and digging into root causes, maybe using techniques like the 5 whys to get to the bottom of things.
That's a very good summary, yes. Curiosity is absolutely key. You could almost think of it as an elegant formula. Science plus technology plus data. Data science.
Hmm.
The science part involves rigorous hypothesis testing, robust methods, logic, linear algebra, statistics, probability, the whole scientific toolkit. Technology covers the powerful tools and automation, things like business intelligence platforms, data mining algorithms, big data infrastructure, predictive analytics frameworks, and machine learning libraries. And data itself, well, that includes both structured and unstructured forms, everything from sensor readings to social media tweets. It's the raw material they work with.
Okay, now here's a common question I hear. How does data analytics differ from data science? They sound pretty similar sometimes. You mentioned they share common ground, like analytical thinking, critical thinking, data storytelling, often using Python. But where's the main difference? Is it that data analytics usually focuses more on understanding historical trends, generating reports, and providing business insights, using tools maybe like Excel, Power BI, Tableau?
That's generally right. Data analytics tends to focus more on explaining the past and present using existing data. Data science, on the other hand, often ventures further into predictive analysis, building and refining machine learning models, and then deploying those models into actual production systems to make future predictions or decisions. Data scientists typically work with more advanced programming environments and frameworks, like Python with specialized libraries, R, and things like Apache Hadoop for handling really big data. But at the end of the day, both fields are aiming for the same goal: communicate actionable insights that lead to better decisions. Data science just tends to involve more complex modeling and prediction.
Got it. And central to modern data science, powering a lot of that predictive capability is artificial intelligence, or AI. John McCarthy, often called the father of AI, defined it pretty simply as the science and engineering of making intelligent machines, especially intelligent computer programs. So AI is like the big, broad umbrella concept.
Exactly. Think of AI as the broadest category. Within that big AI umbrella, you have machine learning, or ML. This refers specifically to algorithms whose performance gets better over time as they're exposed to more and more data, crucially, without being explicitly reprogrammed for every new pattern. And then, as a more specialized subset of machine learning, we find deep learning. Deep learning uses these complex, multi-layered structures called neural networks to learn from truly vast amounts of data. It represents the real cutting edge of AI techniques right now. So it's a clear progression. You start with basic rule-based systems, then move to machine learning, and then deep learning, with each step allowing for more sophisticated and autonomous predictions based just on the input data.
Okay, this brings us to what feels like a really fundamental, almost revolutionary shift in how computers think and operate. What is the core difference between traditional programming, the way we used to think about it, and this idea of data mining or machine learning? It seems like it boils down to this simple yet really profound distinction. Traditional systems work on rules plus data answers, while data mining operates on data plus answers, answers, rules. Is that fair?
That's a perfect way to put it. It captures the essence beautifully. In a traditional programming system, a human programmer sits down and manually figures out and codes the explicit rules. You feed the computer those precise rules along with your data, and the system then just follows the instructions to compute the answers deterministically. So for instance, to calculate the perimeter of a rectangle, you'd explicitly tell the computer the rule. Perimeter equals 2 times the sum of width and height. Give it widths and heights, it gives you perimeters. Simple.
Right, the programmer defines the logic. But with data mining or machine learning, it's a completely different approach. Here, the algorithm autonomously generates or extracts those rules. You give the computer the raw data, the widths and heights in our example, and you give it the known answers, the actual perimeters for those examples. And the system then discovers the underlying rule on its own. For that same rectangle example, it would learn from the examples that, oh, perimeter seems to be 2.0 times width plus 2.0 times height, without anyone ever explicitly programming that formula into it. It derives the logic itself from the data.
Precisely. And this shift is incredibly powerful, especially for tasks where traditional programming really struggles, because the complexity is just overwhelming. Take something like activity recognition, for example. Imagine trying to write explicit if-then-else rules to distinguish between walking, running, or biking, based purely on sensor data like speed, maybe stride length, cadence. It just quickly becomes impossibly unwieldy, trying to account for every single nuance and variation in how people move.
Or even more abstract, think about trying to program rules for clothes recognition from images or face recognition. Writing explicit rules for every possible variation of an image, different angles, lighting, expressions, styles, fabrics, it's practically impossible for a traditional system. And this is exactly where data mining and machine learning just excel, right? They learn these complex, pattern-heavy scenarios implicitly from vast amounts of labeled data. The machine identifies the underlying rules, the important features, the patterns itself, making what was previously just intractable, now achievable.
Exactly. Yeah. That's why Arthur Samuel, way back in 1959, so presciently defined this area as the field of study that gives computers the ability to learn without being explicitly programmed. Microsoft also describes it quite well as using well-researched statistical principles to discover patterns in your data, often calling it predictive analytics or machine learning. At its very heart, data mining is the process of automatically discovering useful information, deriving those implicit rules from data, granting systems the capability to predict future outcomes and make sense of what was previously just unstructured chaos. #tag outro.
Wow, what an incredible journey we've really taken today. From the simplest raw facts like names and numbers, all the way to these sophisticated insights generated by data science and AI, we've seen how data has transformed into really the engine of modern understanding, and the power of data mining especially to derive those underlying rules and make predictions directly from information without explicit programming. That's truly revolutionary stuff. We've explored how data helps us not just understand what happened, but fundamentally why it happened and even what will or should happen next.
It really is a profound shift, isn't it, in how we approach problems and how we interact with the world around us. So, as you reflect on all this, maybe consider this provocative thought. If machines can now learn the rules of the world just by observing data and outcomes, what complex human behaviors or societal patterns might we uncover next? Things we haven't even thought to explicitly look for or program. How might this ability to learn just from observation fundamentally change the way we approach challenges in, well, pretty much every field imaginable? Food for thought.